And okay, so last time we were looking at the type of modulation scheme called PSK, or phase shift keying, right? And basically we talked about BPSK, QPSK, and also the non-binary PSK, which is used for higher data rate in digital communication system. Right? So we were here last time, and I didn't talk about this, I think. And one of the what so basically in any communication system, they will be able to accommodate different data rates. Okay, and in doing so, there are various techniques on how to adapt the data rate in the system. One of them is to modify the parameter m. So you can go from BPSK to QPSK or 16 PSK and so on when you want higher data rate for the user. For example, if the user is closer to the router or is closer to the mobile base station, then the M values will increase, to accommodate the high data rate. When the users are away from the router or they are away from the base station, inevitably the data rate will slowly decrease. And one of the technique is to adjust these M parameters. Okay. During in the next lecture, when Dr. Lin, comes and teach in the class, he will also talk about different technique in adapting the data rate to a finer degree, to a finer uh, steps. Okay, so and for QPSK, which is used for, in this case, in general, QPSK has M is equal to 4 and K is equal to 2. Okay, so there's one variant of QPSK, so-called offset QPSK. So I'm not going to go much into it, but basically what it does is, so if you remember from last time, the signals of QPSK that we send out consists of the cosine and also the sine of the carrier. And this one you can call I channel. This one you can call a Q channel. Okay. So in general, and G is the power shaping. And from last time, one of the power shaping that maybe you remember is root raised cosine, okay, which helps shape the spectrum so that you don't have the second lobe, main lobe, and third lobe, and etc. So for offset QPSK, what they do is instead of modulating the the I bits, the odd bits, uh, and even bits, with the same with the same time shift. What they do is they introduce additional time shift to the even bits or the qubits. So you can call a time shift or additional time delay to the qubits. Okay, and it's a half a bit or half a symbol. In this case, I will call it half a bit. Yeah, it's half a bit time delay. Okay, and so in doing so, this is what happens. So if you look at the next page, on the left hand side, this is the QPSK, and on the right hand side, this is the offset QPSK. For example, let's take a look at an example. If we have the I bits as 1010 and Q bit as 1001. So in general, because we are sending 2 bits at a time in QPSK, so it means that we are sending 11, 00, 10, and 01. And in doing so, we try to match each symbol with the corresponding phase of the cosine that we send. Okay, so for from this example, if you have to transmit 1 1, you will transmit with the phase of pi over 4. And then if you want to transmit with 0 0, what is this phase? What is this phase?
3.014. Oh, sorry.
It's 5 pi over 4. Okay, so in transmission, it is possible to transmit uh, to have a phase jump of 180 degrees or pi radians. Okay, and so this phase change between one symbol to the next of such a large jump, in a way, it looks like an impulse. So it's not very good for circuit design to try to track it. So OQPSK is used to modify such a phase transition. So instead of sending 1010 and 1001, similarly like the left hand side, okay, where they sync, the bits are synced, synchronized to each other. So they introduce this bit delay for half a bit to the qubits. So there's a half a bit delay, okay? So like TS over 2 delay. And in doing so, when you transmit a pair of values, right? So you will transmit 1 1, 0 1, 0 0, 1 0, and etc. Okay, and on the left and here, this is what you can see as the phases that needs to be transmitted on the QPSK signals. So for QPSK signals, you transmit 45 degrees, 135 degrees, and you can jump by uh, 180 degrees is possible. Okay, but then for QPSK, this is what happens. So if you have 1 1, which is what you need to transmit, the next phase, instead of being 0 0, it becomes 0 1. Okay, so there's no such a large phase jump like 180 degrees. The phase jump is reduced to just 90 degrees. And this middle panel, the bottom one, it represents this type of transmitting phases. And you will see that it has some incremental change instead of a big jump like this. Okay. And that's all. And in fact, there are other variation of this type of modulation scheme in order to handle various types of issues as well. Okay. If you have any question, please ask. Two microphone today. I don't have. I just turn on just one session today. Okay. And this is another one. This is called differential PSK, or the. It can be used for binary. It can be used for QPSK, APSK, and so on. Okay. So for this type of PSK, well, they still transmit the phases. Okay, that doesn't change, but it's just how you send the phases, is different. So we send the phase of the difference in bits. So this D represent differential. Okay, that's what it is. So basically, this is what they do for DPSK, or the binary version of the differential PSK. So whenever you have bit 1, we add the phase 180 degrees. Whenever we have the bit 0, we add the phase of 0. Okay. For example, if we take a look at this example, this is very simple with only one cycle per bit. From last time, you notice that for each bit, we have many cycles, right, of the carrier. But here it's just for simplicity. So what they do here is, in here, they use the sine instead of cosine, okay? So it starts with the phase 0 here. And if the next bit is 1, they add the 180 degrees. So instead of starting at 0 here, they start from the the phase of 180s. Okay, so that's what they do. If you have bit 0, so you just keep the same phases as it is. Okay, you just keep what it is, you don't change. Okay, so meaning that we change the phase when we have bit 1. If it's bit 0, we don't change, and for QPSK is similar. What they do here is if you have bit 00, you add phase of phase 0. If you have bit 01, we add the phase of 90 degrees and 180 degrees and minus 80 degrees, etc. So it's not a direct mapping between bits and phase, but for differential system, for each bit or each symbol, you add the phase to the existing pulses. Okay, so basically we add the phases to the pulses, okay, according to data. Okay, so it's different from the typical PSK where we map the bits, we map the data to the phases. But here we don't map the data to the phases. We map the data to the additional phases. So that's the difference. And what do they use this for? They use it in order to reduce the complexity on the receive side. And you will see that in some standards that users move very quickly. For example, airplanes, like aviation. We often see this type of modulation scheme when they have to send some information among each other, and so on. Okay. Okay, so let's take a look at the remaining topic that we left out last time, and this is the last modulation scheme that we will look at, which is called Quadrature Amplitude Modulation, or QAM. Okay? And for this type of modulation scheme, what they do is they modulate amplitude and phases together. Okay, so this is in contrary to uh, the the previous modulation schemes, right? Where we modulate amplitude only, or we modulate frequency only, or we modulate the phases only. But for QAM, they modulate both together. Okay? In the old days, QAM was not so popular because of this varying amplitude, but it caught on. And these days, for high data rate application, both QAM and PSK, they are like the main modulation scheme for how do you say for high data rate application. Okay. So for typical pulses, the pattern is like this. You can write the equation like this. This is the same, but for each pulse I, you have the different energy level. In effect, this is different amplitude, right? Okay, and then for the cosine, also for different pulses I, or the ith symbol. Yeah, you can say this is the ith symbol. Okay, we send different pulses, and it has different phases as well. Okay, and the duration is just one symbol. That's normal. Okay, in order to construct the MQAM, it is simply constructed by two sets of PAM. Okay, for odd bits and for even bits. That's all. So what do we do? For example, if we want to construct a 4 QAM, what we do is we will construct from one set of two PAM, okay, and modulate on cosine, and the other set of two PAM modulate on sine, okay. And from the last lecture, you notice that for the cosine, this is on the horizontal axis, while for the sine, it will be on the vertical axis. Okay. So in effect, the combination of these two sets of PAM modulated on cosine and sine, you have four dots, okay? And this is called QAM. And you may notice that this is quite similar to QPSK from last time, okay? So let's take a look at a more advanced type of QAM, okay? Because like I mentioned, for QAM, we often use for high data rate. Therefore, M is always greater than 2 when we use it. So first, let's take a look at 16 QAM, for example. So let's say for 16 QAM, M is 16. So how many bits do we send at a time? Can anyone answer? So M is 16. What is K?
4.
Yep. Or it's a log n base 2, right? Which is 4. So for this modulation scheme, we send 4 bits at a time. Okay. So out of these 4 bits, okay, 2 bits, we send two sets of we send two sets of 2 bits, okay, at a time. Okay, so one comes from 4 PAM, the other one is also 4 PAM. So that's how we implement it. Okay, so for the I symbol, we transmit 4 PAMs. Okay, and you remember in the past that 4 PAM has the 4 level, right? And for Q symbols, it also has 4 levels. Okay, and so we multiply the Q symbols with the cosine. Okay, and for the Q symbols, we multiply with the sine, and then we subtract from each other. Okay, so this structure, we call this as an IQ structure. This is the last time we also saw in the PSK modulation scheme as well, right? Where we modify the phases by using this IQ structure. So for QAM, it is very similar. We utilize this IQ structure to produce the corresponding amplitude and phases for each pulse or each symbol. Okay, so let's take a look on the left-hand side. Let's say we have this data bit that we want to transmit. So we have to look at uh, 4 bits at a time, right? Let's say this is 1 0. Okay, and because we divide 4 bits into 2 sets of 2 bits, one is, so we'll write out the symbol. So this is 3, this is 1 0 3. Okay, sorry, this is 2, no, this is 2, this is 3 0 and 2, right? And then we use the formula that bi is equal to 2i's minus m minus 1. Sorry, in this case we need to use L. Okay, L. Where here L is the 2 sets, no? So this L is the square root m, which is square root 16, which is 4. Okay, so this in a sense it means 4 PAM. Okay. Wait, let me erase this. It's a bit difficult to see. The reason we don't put M here is because we look at 4 PAMs for each symbols. Okay, we don't look at 16 PAM. Okay, so basically this is bi is equal to 2i's and then minus the 3, right? So this bi, if it's 2, it becomes what? 2 times 2 minus 3, which is 1. 2 times 1 minus 3, which is minus 1, and etc. You get the points, right? Okay, and this will be I Q. So they alternate, when you send it. Okay, so this is like a odd symbols, even symbols, odd symbols, even symbols, and etc. And we send two symbol at a time. Let's say that we want to start sending from these two symbols. We send 1 and we send minus 1 here, okay, together at the same time. So this ST will result into the one of the pulses of 16 QAM, and the amplitude and the phases will vary, accordingly. Okay. Then you can modify this from 16 QAM. You can go to 64 QAM, and all that. If you go with the 64 QAM, then you have M equals to what, 64. We send 6 bit at a time, right? So we have so what this L is equal to square root 64, which is 8. So it means we have two sets of 8 PEM that we transmit. Okay, and that's how we modify it. Okay, we will look at it when we look at Simulink today, when we work on it. Okay, so next let's go to on the receive side. So what do we have? Okay, so on the receive side, we also use the correlator structure as well. So it will be the same as what we saw earlier. Okay, and so for the receive signal that consists of both the I channel and the Q channel, we use the top correlator to extract the I symbols, and we use the bottom correlators to extract the Q symbols. Okay, so that's what we do. This is Q I channel. This is for Q channel. Okay. And as you saw before, that the correlator structure consists of two blocks. One is a mixer or multiplying. Okay, so we multiply the top one with cosine. We multiply it with the top bottom one with a sine. Okay, and then followed by the integration or the sum. And here maybe I change slightly. In here is TB. Let's change to TS because this is a symbol time, not a bit time. Okay, and when you have the output here, let us call Z, Z1 and Z2, for example. So let me put Z1, so that they are different between the top and the bottom one. Okay, so this is, in essence, this is just the condition for 4 PAMs. Okay, because for 4 PAMs, if you have Z at what is it, minus 3, minus 1, 1, 0, 1, and then 3. Okay, so without the noise, it's not difficult to distinguish, but with the noise you set the threshold at the middle. Okay, so if Z is greater than 3, okay, oh sorry, the threshold will be at the middle between the symbols of 4 PAM. Okay, so between minus 3 and minus 1, you have minus 2. Between minus 1 and 1, you have 0. Between 1 and 3, you have 2. Okay, so if Z is greater than 2, then we decide on symbol 3. Okay, if the Z is between 0 and 2, so we decide on the symbol 1. And well, you can see the pattern, right? Then if Z is between minus 2 and 0, we decide on minus 1. And if Z is less than minus 2, we decide on minus 3. Okay, so this condition will be the same for I and Q. Okay, well, and then what and then what else? When you have the estimate for the I symbol and the Q symbol, then you have to convert back to bits, from on the reverse process as we saw on the previous example. So that's about it. Okay. So you can guess that, if I increase from 16 QAM to 64 QAM, okay, so I will have two sets of 8 PAM, right? And each set uh, modulated on cosine or sine separately. So the condition on the receive side for the z, it will be, because you have 8, right? So I think it goes from 4 to 8. So you have to go from -7, -5, -3, -1, 1, 3, 5, 7. Okay. So these are the 8 symbols of 8 PAMs. So it means that the threshold has to be in the middle. Okay. So your conditions will be longer because there are more conditions involved for the decision. Okay. So let me emphasize again, that so I think after you see all these the structure of correlator and all these, and so this is the main difference between the analog communication system and the digital communication system. So in digital communication system, we are not trying to put in the circuit, in order to recover the shape of the signals that has been transmitted. The goal is to make decision. So the key goal in digital communication is to make decision using different blocks in order to reduce the bit error rate or to maximize the SNR. Okay. So the goal for digital communication is never to replicate the pulses that have been transmitted, but to make the decision, okay, in order to reduce the bit error rate or to increase to optimize the SNR, okay, behind A to D, which is behind the masked filter or behind the correlators. Okay, and that's the main difference. But if you look at the analog system or the analog approach, even when it's used in ASK or FSK, the goal is to follow the shape of the pulse, right? Like envelope detection and all that. But for digital approach, it's different, right? We just want to make the best decision as we can. And it goes on and on for other types of modulation scheme and for example. So for 16 QAM, okay, with k equals to 4 bit. So um, last time we also talked about gray coding. Do you remember what gray coding is? Anyone? Does anyone remember what gray coding is? Let me log into another session as well because I cannot see anyone here. Okay. You remember what gray coding is? Tirarat, Pavi, Pio, and others. Okay. Let's look. Don't worry. We have time today. While you are looking, let me actually see something. You remember what gray coding is? Let's look. Don't worry. We have time. I'm always delaying lecture this semester. So, okay. Yes. Tirarat.
Neighboring symbol have one bit difference.
Yeah, that's all. Yes. The symbols that are next together, like this, only one bit different. That's all. Because when we make decision, in general, we make you make the wrong decision to the next symbols next to it. So if there are any errors, only one bit is in error. Okay. If you assign this as one, if you assign this as 0, 1, 0, 0, for example, if you make wrong decision from this symbol to these symbols, see, all 4 bits are wrong. Okay, that's all. I mean, very simple. But then what I'm going to say is that when we talk about PSK last time, there was no exact rule on how to do the gray coding. We just say that uh, we need for the two neighboring symbols, only one bit can be different. That was the only thing we said last time, right? But for QAM, it has a quite a, how do you say it? It has a uh, specific rule on how to construct the gray coding, which is actually very simple. So what they do is for 16 QAM, which consists of two sets of 4 PAM, okay? So the first 4 PAM on cosine, which is on the horizontal axis. So we will label the axis with 4 symbols as -3, -1, 1, and then 3, which are the 4 symbols in 4 PAM, right? And we can assign the bits according to gray codes as well, which is 00, 01, 11, 10. Okay, so this assignment, you can take a look at the previous example. It's just a direct assignment. Okay, but for the horizontal axis, you will notice that neighboring symbols only 1 bit different as well. So that's what we do. But we can assign it similar to the example we saw earlier. When we assign A, we assign B, and so on. Okay. And then for the horizontal axis, we do the same thing because it's also related to 4 PAM. So we have a -3, -1, 1, and then 3, and we assign accordingly that for each symbol we have these sets of bits. Okay. So when we see these 16 symbols in 16 QAM, we can just write out the bits in each symbol as follow. For example, first we start from the horizontal axis, which is 1, 0. Okay. And then we look at the vertical axis, which is 1, 1. So we write 1, 1. Okay. So that's all we do. So the first 2 bits, or the first 2 bits, they come from the x-axis, and the remaining 2 bits, they come from the y-axis. That's all. And you will have and this will be the direct assignment or direct mapping, so that each symbol has the 2 bits, just 1 bit different. Okay. When we say two neighboring symbol, we're talking about these type of symbols that are next to each other. Okay, we're not talking about these diagonal symbols, because the distance here is longer than the distance here. Okay. So let me erase this diagonal distance to you. And maybe you ask me, why do we look into this in so detail? Well, so there are 2 reasons. As you saw last time, that when we look at a whole system with a lot of signals, it's so difficult to look at different phases and amplitudes, right? When you have so many data comes in megabit per second or gigabit per second, it's impossible to just look at the time domain all the time. So if another way of to illustrate is to use the vector plots, then you can see like the quality of the signals, how they how they show on the screen or on the equipment. Okay, so that's the first reason. Second reason is that when you talk about different standard, when you work in a company, they just throw you these vector plots. And when you try to understand some digital physical layer of any system, whether in train signaling, in aviation, in how do you say it, in mobile, in satellite, in and etc. Sometimes they just throw you these vector plots and they just tell you this is modulation. So if you don't understand the reason, how they come about, then you become like a very puzzle, right? Oh, what are these? Okay. So they then sometimes they show formula and then accompanied by this the bit assignment and then vector plot constellation to you. And that's why I think it's important to look at this vector plot as well. Okay, so let me see before we go further. So now we have been talking about 16 QAM for some time, right? Can you tell me, okay, for this 16 QAM, how many different amplitudes are there in all these 16 symbols? And how many different phases are there in these 16 symbols? Okay. To do this, maybe we can consider one quadrant at a time. Okay, let me erase this first so they're cleaner. Okay, so let's look at one quadrant at a time, and I mean it will be the same in all quadrants. Okay, so let us look at the first quadrant, which is Q1 here. Okay, Q1, the quadrant 1. Quadrant 1 only has 4 symbols, right? Which are here, 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 only 4 symbols. How many different amplitudes are there?
16.
No, just one quadrant. There are only 4 symbols. In all these 4 symbols, how many different amplitudes are there? How do you measure the amplitude or the size or the magnitude? You measure how far it is from the center. Okay. So you measure how far it is from here. You measure how far it is from here. Measure how far it is from here. Or measure how far it is from here. Okay. The maximum can only be 4 amplitude, right? Because there are only 4 symbols, right? So for quadrant 1, how many different amplitudes are there? Can you guess from what you saw? What you see on the screen?
4.
No. Mhm. It has to be less than that because 2 symbols have the same magnitude from the center.
2.
2, 3.
It has to be 3, okay? Because let
These
me
are the
erase.
same.
Yeah, because these 2 symbols they have the same magnitude from the center because it has the same length. Yes, but this one is the shortest one, right? Right, and this one is the longest one. Okay, so there are only 3 different amplitudes, different or 3 different magnitudes. Okay, okay, or you can say 3 different envelope. Yeah, let's say magnitude maybe is better. It better than amplitudes. Amplitude is at each time. So let's call magnitude, no? So that is more precise. One moment, let me. Okay, let's call magnitude, no? Magnitudes. Okay. So 3. How about number of phases? How many phases are there? How many different phases are there? Phases means angles. Okay. Yeah. In this quadrant 1, okay, how many different angles are there?
3,
No. Maximum is 4.
3,
No. Mhm.
3, 1.
Oh, sorry. You're right. 3. Yeah, you're right. Three. Yeah, it's three. Because this symbol and these symbols, they at about 45 degrees, right? Okay. But this one is about 30 degrees. This is about 30 degrees, 60 degrees. So there are also three faces. Okay. And then how about Q1? Oh, no, Q2. Okay. Well, if you look at all four quadrants, the magnitude will be the same as in Q1, right? And the magnitude in Q3 will also be the same as in Q1. And in Q4, also the same, okay? So in general, we say that number of different magnitude for 16 QAM is only 3, yes. But for the phases, different quadrants, they have different angles, okay? So for one quadrant, you have 3 different phases, but for 4 quadrant, you have 12, which is 3 times 4 phases, okay? So if you draw the signals in time, this is what you will see, but we will see later when we look at Simulink. Okay, I think I forgot to send you the Simulink demo today, but let me do it after this. No. So this is 16 QAM. Okay, so let's take it. Oh, it's almost 10 already. Shall we have like a 5-minute breaks maybe? Okay. So you can rest a little bit. We will not go to Simulink let me think, should we go to Simulink right away, or let us go to Simulink at the end, because you have to send to work on it and then send it back as well. No? So let's have a 5-minute break, and then when we come back, we will look at the remaining slides and then followed by the Simulink software. Okay. So you have any question so far? And you can guess, this modulation, they can extend further and further to m is equal to 64, 256, 256, 512, or 1024. And this is true, for communication system that needs high data rate in satellite, in internet at home, they all have very, very large constellation in order to accommodate such a high data rate service. But for ASK and FSK and for BPSK, they often use in very low data rate applications, that you don't need such a high data rate. So they're different, like domain we have to look at these days. Okay, let's have a break for 5 minutes and then come back. Okay.